Hello, and welcome to the role of uncertainty for today's microwave and millimeter wave measurements with Dr. Andrea Ferrero. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by the MTTS Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Dr. Andrea Ferrero received a PhD in electronics from Politecnico di Torino in 1992. He then joined the Hewlett-Packard Microwave Technology Division in Santa Rosa as a visiting scientist and also started as an assistant professor at Politecnico di Torino. He made his way through the academic ranks at Politecnico di Torino, winning various awards and teaching electronic instrumentation and measurements and microwave instrumentation and electronic and telecommunication engineering until 2012. In 2013, he joined Keysight Technologies as a principal research engineer. Dr. Ferrero is a member of Technical Committee 11 for microwave measurements, has been an MTTS Distinguished Microwave Lecturer, and is also an IEEE Fellow. Since 2017, he has been an associate editor of the Transactions on Microwave Theory and Techniques. Dr. Ferrero is the co-author of over 100 papers on microwave technologies and measurement techniques, and his current interests are focused on device characterization, calibration techniques, and VNA metrology. Finally, you may be interested to know that he's also a competition glider pilot with more than 29 years of activity flying gliders and small airplanes, and also working on avionics, microwave, and EMC problems. So now it's my pleasure to turn the virtual podium over to Dr. Andrea Ferrero for the role of uncertainty for today's microwave and millimeter wave measurements. Andrea?
Good morning, everybody. Thank you very much, Mike, for the introduction. So let me see if this thing is working now. Okay. So today we're going to talk about technique for enhancing the accuracy and computing uncertainty, and in general, what the uncertainty play in the role of modern microwave and millimeter wave measurements. So this is the agenda of the talk. First of all, we're going to give you a small introduction, and then we will talk about uncertainty and S parameter, followed by uncertainty and power measurement. Then we will draw some conclusion. So why uncertainty accuracy is a must? Well, accuracy is directly linked with the customer satisfaction. Why so? Let me make some small example. The accuracy has a direct impact on the business. Look why. So let's say that we have some test, and the test can have a pass or fail. But the true state of the product can be good or bad. Now, if the test is passed, but the product is bad, we find this case where we have an enormous increase of return rate and warranty and cost. We all remember the big blast when, for example, Apple has to bring back all the iPhone 4 due to the wrong problem with the antenna. But there is also another case when you have the test which is failed, but the product is good. So in this case, the costs are due to false failure. So we have costs associated with the wrong outcome of the combination of the two states of the product and of the test. And those costs really needs to factorize. So how this is dependent with the uncertainty? Well, clearly, if you have let's say that you have a product and this performance has a plus minus 1 dB of uncertainty, you will have a certain yield. If you are able to reduce the uncertainty to 0.25 dB, then you will have another yield. So clearly, this cost associated with the fault test will be directly linked with the uncertainty. You can directly make math computations such as, oh, if I have such a yield, I will have such and such cost. If I can reduce the yield because I can improve my measurements uncertainty, I will have such and such cost. So it's fundamental to study and to have the knowledge of what uncertainty is. So let's come through the vocabulary. So what's a measurement first? Well, a measurement is the process of experimentally obtaining one or more quantity value that reasonably can be attributed to a quantity. We all know that, but what does exactly mean? What is the uncertainty? Well, uncertainty is a non-negative parameter characterizing the dispersion of the quantity value being attributed to a measurement based on the information used. These are the definitions for the International Vocabulary of Metrology. Now, there is another fundamental part which is many times confused with uncertainty, which is called systematic error. What's the difference between systematic error and uncertainty? Well, the systematic error is the component of the measurement error that in replicated measurements remain constant and varies in a predictable manner, which means that a systematic measurement error can be corrected. And so a correction can be applied in order to compensate the systematic measurement error, while you cannot compensate for the uncertainty. The uncertainty is what it is, while the systematic error can, in a certain condition, correct it for. Now let's come to a more close definition of uncertainty. So this is more familiar to everybody, right? We have a set of samples of a process of a measurement, and we define the mean value, and we can introduce the distance from the mean. And if we have the distance from the mean, we can compute the variance as a sort of the mean of the distance from the mean. Clearly, this distance is defined as xi minus x averaging square and all the sum, and this is always positive. So, however, there is some more probabilistic way to look at the uncertainty in terms of probabilistic distribution function, probability distribution function. So I hope everybody remember these things that you can have within the set of samples, some samples that are close distributed to the mean, and while some other are way far from the mean. So clearly you can have a distribution, and then how we can define the uncertainty? Well, the uncertainty can be defined as the spread of this distribution, and in particularly a link, if the distribution is Gaussian, as in this case, link with the variance of the distribution, which in this case, if we have 1 sigma is the variance, then we will have the 68% of the sample falling into the interval defined from averaging minus 1 sigma to averaging plus 1 sigma. Then in the case of 2 sigma, we will have the 94.5%. In the case of 3 sigma, we will have the 99%. So clearly, it's up to us, say, I want to be sure of the 99% that my samples will fall within 3 sigma. Then in this case, I will have a certain uncertainty defined with a coverage factor of 3. If I want a more, let's say, having a probability that only 68% of the sample falls into the interval defined, then we will have just to consider 1 sigma. So as you can see, the important number is the variance. Then the uncertainty is defined as the variance times the coveraging factor. Typically, 2 sigma is a good number for the coveraging factor. We could start a long discussion about the kind of distribution, but I would prefer to concentrate our attention on what happens when you have a multivariable uncertainty. So when we have a function that has 2 variables and which determines the output. So in this case, Z is our output and X and Y are our input. Then how we can compute the uncertainty of Z if we have X and Y? Well, we use the fact that uncertainty is a small number. So if the uncertainty is the small number, the delta can be easily computed as the sum of the partial derivative times the variation of X and the variation of Y. So in other words, the weighted sum of the variation of the input. We can write this equation as a vector times a transpose vector, and now clearly Vz will be delta Z times delta Z transpose, as we have done before, which if we go on, we have now delta Z, which is this part, delta Z transpose is the same vector, just transpose. And now look what happened. We have what we call typically the Jacobian, so the sensitivity of the output versus the 2 input in this case. But also we have the Jacobian here and the Jacobian transpose here this side. But we have a new entity here, which is what we call variance matrices. Look what variance matrices here. So the variance of X, the variance of Y, and the covariance. And the covariance. So the covariance element is defined as the averaging of the product of the distance between the X variable and the Y variable. Now, I'm used to explain what the covariance is because everybody understands what the variance is, right? We just seen that with the case of the probability for one simple variable. But what is the covariance? Well, the covariance explains the effect on Z of the interaction between X and Y. So Z will be affected not only by the uncertainty of X, not only by the uncertainty of Y, but will be affected also by their interaction, which is expressed by the covariance. Let's come to another important case, which it's, in my view, a little bit underestimated. In our field, in microwave fields, we are dealing with complex number. Now, how we can quantify the uncertainty of a complex number? How is the uncertainty of a complex number? Well, in the complex number, we will definitely have a covariance matrix. Why? Because we have, for sure, the uncertainty of the real part, the uncertainty of the imaginary part, but also their interaction. So we have, this is the case, Gaussian plane, we have our complex number expressed as a vector. And we can see that if we have uncorrelated uncertainty, and in this case I also put them equal, then we will have a circle around the nominal value. This is the classical, I would say, representation, but it's not enough. This is not what we really need to make a proper uncertainty propagation in the complex domain. Why? Because what we have is the correlation. What we have is the correlation effect. The correlation, and furthermore, we also have that the variance of the imaginary is not the same as the variance of the real part, which means that this circle is no more the circle, becomes an ellipsoid, and the ellipsoid gets tilted. This is an example of the simulation of a random Gaussian point for a complex number. As you can see, we have the variance matrices, and they clearly region now is defined as an ellipse. So let's come to introduce the process of determining the uncertainty. We have just seen what is the uncertainty, so now let's come to introduce the process of evaluation of the uncertainty. First of all, you need to develop a measurement model. A measurement model is a mathematical relationship between what you want to know and what you can know. What you want to know may be whatever. What you can know is typically the output of an instrument. They are nominally related, typically related by mathematical relationships. And this is what is called measurement model. Then you need to develop methods to characterize the uncertainty contribution. In this model, there will be some quantities that they will have some uncertainty. So you need to characterize them to know them. So you can do that by, I can look at the data sheet, for example, or I can make repetitive measurements. Whatever the process is, the process has to be able to compute the uncertainty contribution of the various input quantities. And then you have to propagate the uncertainty contribution in a fully correlated way. So let's make an example. Here we have a simple voltage divider. Now let's suppose that we have R2, which doesn't have uncertainty, so it's a constant. R1, which have uncertainty, and E, the input voltage, also has uncertainty, and they both are related to each other. So we want to know the output voltages and its uncertainties. So the model in this case is trivial, right? We all know that. E2 is equal E times R2 divided R1 plus R2. Great, so this is our model equation. Now, suppose that we know the uncertainty of R1 and E, which is expressed in terms of their covariance matrices. So in these matrices, we have the variance of E, the variance of R1, and their covariance. Supposedly that we have found a way, or we have, for example, just look inside the data sheet and have the capability to build these matrices. Now we do the third step, which is propagate. So we compute the Jacobian, and we compute the final variance of the E2 by doing the Jacobian times the variance matrix times the Jacobian transpose. As you can see here, the variance of the output is not just the weighted sum of the variance of the two inputs, but it also has a covariance element. And the covariance element, which express the correlation between the two, may reduce the total variance of the output, or in other words, may reduce the uncertainty of your output. Or you may overestimate the uncertainty if you just sum weighted properly the two uncertainty of the two inputs, because their mutual effects can reduce the final uncertainty. And this is something that people tend to forget, because at the beginning of the development of the metrology science, there was not enough computing technology to propagate this uncertainty properly. As you can see here, to propagate the uncertainty, I had to compute the partial derivative, do a matrix multiplication, actually two matrix multiplication, to do them properly. While if I do forget the correlation, I could just make what is called RSS, uncertainty estimation. Today, though, there is the computing technology that allows to do uncertainty computation in a fully correlated way. So as I said, for complex models, the Jacobian may be very difficult to calculate. Today we have two numerical methods that are common. The first of all is the Monte Carlo technique. I bet everybody is familiar with that. It is simply just try every possible combination of the input parameter to obtain to obtain the output things. Then, so it's easy to understand, although it's very slow, and it has an advantage slow, that it offers the entire view of the probabilistic problem. So if you have input quantity which has a different kind of probabilistic distribution function, with the Monte Carlo technique, you can simulate the effect of that. However, when the problem becomes very complicated, the Monte Carlo technique becomes too slow and may not converge to the proper solution. The other technique, which is maybe less known to you, is the automatic differentiation. The automatic differentiation is based on modern C++ software paradigm, which is called operator overload. I will show you in a little bit in the next slide. However, it does not compute the output probability distribution function, but it's slow compared to the analytical approach, but it's much faster compared to the Monte Carlo technique. The analytical approach is what I just showed you in a slide before, so the analytically compute the partial derivative. So let's look at an example of automatic differentiation. Fortunately, today there is a library available which is called Meta's Uncertainty Library, a free library in MATLAB, which allows you to compute uncertainty on any quantity you want. So I just show you, I found out that to show the effectiveness of this technique would be much better just to give you an example of the code. So this is our voltage divider. As you can see here, you set E as something which is strange, which is UNC, which is an object, a MATLAB object that has 10 as nominal value, and the uncertainty which is the square of 0.06. R1 is 4 as nominal value, and uncertainty is the square of 0.016. Then R2 is our constant. Finally, you put the model equation into. So you see here there's no Jacobian computation, there's nothing. You just call a function which is get covariance. So no need for analytical derivation, and you get the proper propagation of the uncertainty as well. It's super easy to use and allows you to solve the problem and to avoid analytical derivation of the Jacobian. This technique has been successfully applied to compute the uncertainty for many, many cases in metrological world, and in particular also to the uncertainty of S parameter. Why uncertainty of the S parameter is fundamental? Because the S parameter are the fundamental block of all microwave measurements. So they are fundamental for power. They are fundamental for gain. They are fundamental for mixer measurements. And they are also fundamental for noise. Why I'm talking about uncertainty, let's switch to S parameter immediately. Because the uncertainty model requires the knowledge or the estimate of S parameter, even if the instrument does not directly measure them. Let me explain this concept. Let's say that you have a simple power meter. Well, to compute the uncertainty of a simple power meter output, you need to know somehow the uncertainty linked with the reflection coefficients, transmission coefficients, which are S parameter. And thus, the uncertainty of the final power will be function of the uncertainty how you estimate your S parameter. In this talk, I'm going to talk about VNA. Why I'm talking about VNA? Because VNA is capable to perform in vector corrective measurements. Thus is the main instrument to perform the most accurate microwave measurements. In the case of a simple power meter that I was saying before, you get just the information about the power, but since the measurement system is not able to compute vector measurements, you have to estimate the uncertainty by other means, by knowing S parameter somewhere else, and you can only guess the amount of reflection uncertainty given by the match of your power meter and your amplifier, for example. While if you do the measurements with the VNA, Since the VNA is able to perform in vector correcting measurement, well, then is able to perform the most accurate measurement. The beauty of using the VNA is that the measurement model is fundamentally the same for S parameter as well as for any other extra measurement which the instrument is capable of. Thus, the accuracy of any VNA measurement strongly depends on the accuracy of S parameter calibration and measurement. So I'll give you an example of what I'm talking about. So let's come to a one-port VNA. A one-port VNA it has a relatively simple scheme. It has a synthesizer, a source, and then it has two mixers, and then it has a digitizer. So, and then it has some couplers. So the VNA acquires the IF at the mixer output, AM, R, and B, M, I, the reference and the test. But what you want is computing AI and BI at the reference plane. Now, what are the VNA fundamentals? The VNA is a swept frequency measurement, so you can have directly frequency measurements all over the one measurement frequency sweep all over. You have coherent measurements. So in other words, you have vector measurements. It's a linear measurement system, but obviously you can measure anything with that. It's a highly linear measurement system. It has a high dynamic range, and it has an ultra broadband. However, it has a huge systematic error, which then imply a sophisticated calibration technology. This is an example of modern VNA. This is a modular multi-port VNA. As you can see here, each module has 2 ports, and then you can plug together up to, in this case, 16 modules to reach 32 ports, for example. Or you have an ultra-wideband scheme where you do have some extender. So as you can see here, again, a source, 2 couplers, 2 receiver, but then you put some extender to reach millimeter wave and go up. Or you have the case where the system becomes one box, many instruments. I said that because as you can see here, you have 2 sources, for example, some pulse generator, 4 ports, of course, 8 receiver, and you can configure this box to be able to make, for example, power measurements, pulse measurements, noise figure measurements, and so on and so on. So in other words, the same concept that we just seen built from 1 couplers and 2 receiver has been expanded in the years since the 60s when it was invented to a much more complicated, ultra versatile system. However, the systematic error is always there. And the systematic error, the correction of the systematic error is what makes VNA measurements absolutely ultra accurate. Let's see what we are talking about. So imagine to go to a grocery store, and then you have a balance, and you want to buy 30 grams of prosciutto, but the balance has a 1-ton plate. You may ask yourself, do you trust the grocery man? Do you pay for the 30 grams or not? Well, let's come, or you may ask yourself, what are you talking about, Andrea? Well, let's see in 1 minute. So the weight of the ham, which is what you were looking for, and the weight of the plate are 30 grams divided 1,000, which means 3 times minus 5. Now let's take a VNA, our 1-port VNA, and had a 1 meter telephone cable. We want to compute the phase of our gamma. So we want to measure 1 degree of resolution, the reflection coefficients at the data reference plane, but we have the cable in the middle. So it's simple to compute the effect of the phase shifting caused by the cable. So we want 1 degree, and all the rest is 2 times 360 times telephone cable, 2.31 epsilon r. And the final result is the same as we were in the grocery store. So you immediately understand that unless you make a calibration, VNA measurements are completely untrustable. The phase of any VNA measurement is completely random if you don't make a proper calibration. Looks randomly, actually, because you have a huge systematic effects given simply by the cable. So what the calibration does? Well, the calibration correct for the reference plane, as we just said, and the reference impedance. Because remember, the output of a mixer is just memory location. You want in reality to measure some reflection coefficients referred to a certain reference impedance. So how does the calibration work? Well, the calibration works exactly as in the grocery store. You have to put some known device. And so the off grail of a calibration would be something that does not require a standard. Should be fast and simple, and should be accurate. However, as in the grocery, you can easily understand that you need at least one standard, because you need the reference impedance knowledge and you need to move the reference plane. So how the calibration works? The VNA is assumed linear. So we start from some raw measurements. Then we plug the error coefficients, the calibration coefficients, and we obtain the corrected measurement. Since the system is linear, this operation is a linear operation. How we compute the error coefficients? Well, we have some standards which are given by some models, can be electromagnetic or can be mechanical with the electromagnetic analytical model. Then we do some standard measurements and we compute the calibration coefficients out of them. This is exactly the same as you want to calibrate a balance in our grocery store. There are many algorithms to compute the calibration, but the principle stays the same. Measure some known device, compute the error coefficients, and correct the raw data. Now let's come very briefly to our one-port VNA model to see what it is. So this is the VNA, a two-port VNA. So in this case, you have when the source is connected to the port 1, since you have two outputs, A and B, and you have two inputs, BM and BAM. So this is linear. You will have 4 coefficients. In the case when the source is not connected to the port, then in this case you can just read one output, and you always have two outputs, A and B, and you just have one input, which is the reading of the one mixer there. So you have 6 coefficients, which are related to the directivity, the source match, the reflection tracking, and the load match. However, this thing shows clearly the linear dependencies of the input versus the output in a very simple way. This model is called a two-state model. So if you generalize these things into matrix form, then you can write an equation which links the error coefficients, A, K, L, M, in the form of matrices, the measurement matrices, and the weight matrices, A and B and A and B, which of course, if you look at the S parameter traditional equation, will link the S parameter of your unknown device. These relationships is both linear in the error coefficients and in the measurement. So you can use that for the calibration if you know S, or for the measurements if you know the error coefficients matrices, A, K, L, M, F, G. It's valid for any number of ports, it's very flexible, and is always defined because the S parameters are always defined. So you can use it for a short, for a load, for an open, everywhere. So now let's come with the S parameter with uncertainty. So in the case of uncertainty, we have exactly the same model, but we have to add uncertainty. In this case, we're going to add uncertainty in the form of noise, in the form of calibration standard uncertainty, and in the form of repeatability. So let's start from the repeatability. So the repeatability can be modeled in terms of a random path attached to our VNA, which of course has some random number in the reflection, a random number on the transmission. Since the interface is small, we can assume the variance of the reflection coefficients, the variance of the transmission coefficients, and their covariances. This is an example. So as you can see here, we have, maybe you cannot read it, but the level here is minus 60 dB. And this is the example of an uncertainty the reflection coefficient, or the reflection variance at the test port of the VNA and at the end of the cable. As you can see, they look quite different, and the one of the cable has a much higher uncertainty associated, which is normal. The variance, the cable has a effect on the uncertainty because it changes, it moves, and so on, and these variance reflects, these plots reflect exactly that. If you make the measurements at the VNA test port, you have a much less influence because you do not have the cable. So now let's move to the noise. The noise is modeled in a well-known way, so with a trace noise and some noise floor. And so the variance of our reading, in this case any reading, will have a variance due to the noise, trace noise, and the variance due to the noise floor. This is an example of noise example. Again, here read, for example, minus 100 dB. So this is to show you that the uncertainty is a small number. We have to deal with a small number. However, since the accuracy required in our test is getting more and more stringent, the small number given by this kind of uncertainty may play the role. So let's come to the third effect, the calibration standard. So in order to do that, we can do a Monte Carlo EM simulator, or we can do database modeling. Or we can have transfer standard. So what a transfer standard is what typically we call the ECAL, so the electronic calibrator. This is a transfer standard, so a standard which has been measured with a VNA calibrated by the golden metrology standard, which is what we call a golden line, and the most precise calibration possible. This is an example of a two-port uncertainty with S parameter. S parameter of two ports with uncertainty. As you can see here, we have, for example, in this case, an uncertainty of about 0.1, 0.2 dB, which is fairly common. But as you look at this level, the uncertainty becomes bigger and bigger. Why? Because when you go down at minus 70, minus 8, then the uncertainty increases due to the noise effect. So if for high level signal, the uncertainty can be 0.1, 0.2. For the low level signal, the uncertainty can be dBs or even more than that. So now let's move out of S parameter in the last 5 minutes to look at what we can have in terms of power measurement, how we can obtain accurate power measurement. Well, VNA can be used as selective power meter, which means that we have a huge dynamic range, it's extremely linear, and it's tunable. However, it requires a power calibration for doing that. So the overall uncertainty then will be function of S parameter calibration, S parameter measurement uncertainty, and the power meter uncertainty transfer to the VNA. Because to do the power calibration, you have to set the absolute value of the power of the VNA reading by means of a power meter. So typically you attach a power meter to one port of the VNA, you measure the absolute power with the power meter, you make the reading with the VNA, and that is how you calibrate the VNA for absolute power. The beauty of using a VNA for power is that this is an example of how we can have a power of a device reference plane where we want the power at the device plane, but in reality, we are out of where we can put a power meter into. Because the power meter can be put at the coaxial interface, but not inside. So now these three plots show that without the correction, P out at the measurement plane, so here, and P out at the device plane. Because by using a VNA, you can de-embed in the proper way anything there is between your measurement plane and your device plane. This is another feature that with the power meter you cannot do that. So let's come to a little bit more detail to how we compute the power meter measurement. So for example, if we have the power meter has a measurement model which is traceable to the microcalorimeter, for in this case of an IST, then it goes toward your device and your sensor. You have uncertainty codes, which are given by the power meter reading, the sensor efficiency, the power of the generator, and so on. With the VNA, this is the model that you have to use when you have a VNA. So you have the reading of the VNA, in this case AM1, and you know you have gamma in, and you have the source match in this case. So this is the equation, not this C1. C1 is the coefficient I talked to you before. In order to compute C1, you have to make an absolute power measurement, which means you have to put, rather than your device here, you have to put your power meter. The power meter compute is known now. AM obviously is known. All the rest come known. And what you get is C1. Now, clearly, if you use the Metas uncertainty library to compute the uncertainty on the pin, would be straightforward. And that's exactly what we have done. So this is given by the power card, and this is an example of the uncertainty given by on the power given by a VNA. As you can see, the level of the uncertainty is 0.1, 0.2, but that's exactly the kind of uncertainty that you have to expect when you're talking about power. So anything below 0.1, 0.2 in terms of absolute power is absolutely not realistic. Remember that these measurements include the vector error correction, include the proper standards, and include the uncertainty of the power meters properly computed and propagated. So in conclusion, the proper uncertainty evaluation reduces the cost of all the development phases. As parameter uncertainty tools are now a reality, you can compute the uncertainty on S parameter relatively easy. And then you can extend them by using modern techniques in MATLAB or equivalent software. So this concludes my talk, and now I'm open for questions.
Great, thanks a lot, Andrea. That was a really informative talk. So now it is time for our question and answer session. Before we start that, remember that you can still submit questions through the Q&A panel. We just have a limited number right now, but please feel free to submit your questions. So now here's the first question. So is it correct to state that for current performance network analyzers that the uncertainty on the calibration elements, presumably the standards, is the largest contribution to the overall uncertainty for S parameter measurements?
Yes and no. In other words, it really depends on the level of the signal that you're talking about. So if you have, for example, let's say that you have a filter, and the filter has 100 dB stop band. Then when you're going to measure the stop band, then clearly in the stop band, the noise of the VNA will play a bigger role. But when you measure the parameter on the passband, within the passband, then definitely the calibration will play the bigger role. So there's no unique answer. It strongly depends on the kind of the device that you are measuring. I hope to answer your question, Franz.
Okay, yeah, definitely. And just a reminder, please feel free to submit whatever questions you have. We've got an expert on VNA measurements and the associated uncertainty, so please submit your questions. Let's see, here's a new one. Does the automatic differentiation using MATLAB routine that you mentioned, does that require any special MATLAB toolboxes or just standard MATLAB?
Now you just have to answer. You just have to download you go on the website. I write it here. You go on Meta's website and look for Meta's untlib. And look of Meta's uncertainty library. If you look for Meta's uncertainty library, you can freely download, no registration, nothing, it's fully free. You can download the package, you run it in MATLAB, and it's a straightforward usage. I mean, it's very, very simple. And you can use that to compute uncertainty on everything. I use them every day to verify my computation. Within our VNA, we do analytically because we want to go very fast. We do analytically uncertainty evaluation. But for testing, then I'm going to use that because it's I'm using that because it's so easy.
Okay. Okay, great. Okay, so here's another question. Actually, I was thinking this question myself. So how can we know the uncertainty, or what types of uncertainty can we expect for measurements of resonant frequencies and quality factors for microwave resonators?
Oh, this is something that this is exactly the case where the matrix uncertainty library becomes very effective. So what I would do if I would have to measure the quality factor of a resonator, I would make a VNA measurement with uncertainty. So S parameter with uncertainty on top of that, and then I will compute my Q factor from the S parameter using the matrix uncertainty library. In that case, in that way, I can export the S parameter uncertainty from the VNA, and then I can load them inside the matrix uncertainty library and compute the Q factor with the traditional formulas without worry about propagation, because the uncertainty library will clean my propagation. At that point, I will get the uncertainty that I can exactly have by measuring my quality frequency, my resonation frequency and quality factor.
Okay. What would be the sources of uncertainty for that?
Oh, the sources of uncertainty is linked fundamentally to the model of the uncertainty of the S parameter that I showed to you. So you will always have like calibration, repeatability, noise. You may have other causes, but those are the three main big players. You may, for example, if you make the calibration now and you make the measurements tomorrow, then you will have drift to account for. But I would highly discourage to do that. So if you want to make accurate measurements, make the calibration now and make the measurements now, right after, not wait 1 week or 1 day or maybe turn on and off the instrument, because that will completely increase your uncertainty just by the drift of the system of the instrument itself.
Sure. Right. Okay.
Okay. Have a power
yeah. So do you have a power measurement uncertainty using the VNA method plot versus UT match?
Oh yes. Well, the using the I don't know if I can share. Let me see if I can share. Come back here. So this plot, for example, has been obtained by directly measurements of the power with a VNA. So if we did this plot include clearly this plot. You can read this plot as like A1 absolute. I don't remember exactly if it's A1 or the P in. I believe that this is the magnitude of A1 absolute. So the beauty of the VNA is that you have access to all of these quantities, A1 and B1. And you have the absolute access to all of them with their uncertainty. So you can compute whatever you want. In this case, I compute A1, 1 minus gamma in, but I could compute whatever. If you're thinking about it in a multiple way, I can compute anything. So to answer the question, do we have, oh wait, one second, where are the questions? Do we plot versus UT match or not? This is up to you. I mean, the VNA compute the uncertainty on each waves. You can compute the uncertainty on the waves, but then you can include or not the match depending on what you want to know. So it's like I know I have the uncertainty on all the voltages and current. I can compute whatever I want. Okay.
Are you there?
Is it is it answered? I mean.
I believe so. The question may actually be asking specifically, do you have that information, or could you provide some information about that?
What I've done is in my case, it was using information out of the S parameter measurement uncertainty and couple them with the power uncertainty to compute the uncertainty on the power. I purposely decided to put uncertainty on the power to show to you guys how you can use what we have commercially available, so technology for computing uncertainty in any case, coupled with technology for computing uncertainty on S parameter.
Right. Okay. Okay. We do still have time for another couple of questions. If anybody has any questions, please feel free to submit those. Or Andrea, we've also, we've got a few minutes left here. Were there any other comments? I guess one question would be, how does this extend into the realm of nonlinear measurements?
What did you say?
So how would these concepts extend into the realm of nonlinear X parameter type measurements?
Oh yes. Okay, so you have to think about yes. Wait one second. I'll just give you an example of what we're talking about. So this is the model of the VNA, right? So the VNA provides information about A and B at different frequencies at the reference plane. Now,
hold on 1 second. The live slide shows noise uncertainty. Is that what you want to show?
Yes, noise uncertainty, calibration standard uncertainty, and repeatability uncertainty. This is what we have, what we include. There are, as I said, for example, there is drift, but I would highly discourage the way that the instruments derive to make accurate measurement. Do the cal, make the measurement. Otherwise, really, let's say the temperature change, then your measure is screwed. So now, suppose that you have, this model is already enough complicated because you have to propagate all this information. For example, when you make the measurement, the noise affects the measurements directly, but also the noise affects the calibration coefficient, so which in turn affects the measurement. Now, suppose today, the technology today allows us to compute uncertainty on S parameter and on waves at the DUT reference plane. Now, to compute uncertainty on X parameters, on the nonlinear part, then clearly you have to take into account the fact that you have multiple phasor. You have to combine, because to compute the nonlinear effect, then you have to typically do, for example, an FFT. And in that case, it's not frequency independent. Now, if you think about, let's say that I have like 1,000 frequency and I have frequency independent, then I have 1,000. I don't have to take care about the correlation among frequencies. But if let's say I want to compute time domain response, for example, and I just have to compute FFT. Then if I want to make an FFT, then I have to compute the uncertainty between frequency and frequency. And this means it explodes. The amount of correlation that you need to take care simply explode. If you remember the first slide, when it comes to here, so 1 second. So here. So in this case, we have two quantities, E and R1, which are correlated. And so which means that we need to carry around 3 numbers, an uncertainty of E, uncertainty of R1, and the correlation. Now, if you would have not 2, but 3, then it would be 9 number, actually 3 by 3. Then, of course, it's symmetric, so you can avoid the lower part of the matrix. But if you have 1,000 number, then you're going to have 1,000 times 1,000, the entire correlation matrix. So you understand that this is not something that you can solve in a snap that it works it has some computing power. Actually, this is why we are doing fully correlated propagation today, because before we didn't have enough computing power, but still we cannot correlate everything. It's the problem of the butterfly in Australia, right? You cannot correlate everything. You have to stop at a certain point. So today we decide to stop at the S parameter point, and we are adding power right now. But clearly, to achieve the nonlinear, I need a little bit more computing power than what we can reasonably have today. So my answer to the nonlinear things is it will come. Maybe not in my life, though.
Okay, all right. It's a lot more complex.
Yeah, it's a lot more complex. I heard this question many times. I mean, the problem is that I cannot do these things and say, oh, wait 1 month before getting the answer. I have to provide an information reasonably fast. So there have been attempts, there have been some publications, some paper of computing the uncertainty on X parameter, but they have done like, okay, we do it once with a PhD that makes 1 month of Monte Carlo simulation to achieve that. I'm not saying that you cannot do it. I'm saying that we have to do it in a reasonable way such that it's useful. So today, VNA can produce plots like this. So I want to show you. I can produce a plot like this because it's S parameter in real time. I'm not yet there to produce a plot on X parameter for nonlinear measurement in real time.
Right, okay. Okay.
Oh, okay, to do my question, can the VNA show the PN uncertainty plot by user choose with the factory provide? The answer is the PNA right now, today, cannot show the PIN. You can do that by using the PNA and using some purposely made MATLAB code to compute the PIN. With this MATLAB code, use the Methods Uncertainty library.
Okay, and just to clarify that for the users that can't see the question, the question is asking, can the VNA display the uncertainty plots, just readily display them, or essentially does that need to be done in post-processing? And I think the answer is it has to be post-process, right?
It has in post-processing, but see, for example, this is real time, so this is the real screenshot of the PNA. This is not in real time. This is done in MATLAB by myself. Okay.
Oh, okay.
However, I can tell you that the problem of putting the power is a much simpler problem than the problem of having X parameter, which means that stay tuned. Let's put it this way.
Okay. Well, that's great. I think that's a great place to finish this off. We're right at the end of the time here, so we are out of time. We really appreciate Andrea for answering our questions. And as we said earlier, this session will be archived on the Society website at mtt.org. All the registrants will get an email reminder with the website address when that is available. For attendees who would like to receive PDH credits, please follow the link in the webcast window view and use the code that's provided on the last slide of the presentation, which is displayed right now. Once again, I'd like to thank Dr. Ferro for this excellent and informative presentation. Special thanks also to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you and have a great day.
Everybody. Thank you very much, everybody. It's been a pleasure for me to stay with you today. So, Michael, I can log off on what I'm going to do?
Just hold on real tight.